Every generation of combat aircraft has been defined not just by its airframe or its weapons, but by the engine that powers it. The jet engine that Frank Whittle and Hans von Ohain independently invented in the 1930s made the first generation of jet fighters possible. The afterburning turbojets of the 1950s enabled the supersonic age. The high-bypass turbofans of the 1970s gave the F-15 and F-16 their extraordinary thrust-to-weight ratios. The low-bypass augmented turbofans of the F-119 and F-135 gave the F-22 and F-35 their supercruise and stealth-compatible performance. And now, a new engine architecture, the adaptive cycle engine, is being developed that will define sixth-generation combat aviation. This is the engine that will power the F-47, and its engineering represents perhaps the most significant advance in jet propulsion since the invention of the turbofan itself. Leave your like, subscribe, and share. Let's begin. To understand why the adaptive cycle engine matters, you need to understand the fundamental tension at the heart of every jet engine design. A jet engine produces thrust by accelerating air rearward, and the thrust it generates depends on two things: how much air it moves and how fast it accelerates that air. A turbojet, the original jet engine architecture, accelerates a relatively small amount of air to very high velocity. This produces high specific thrust, which is ideal for high-speed flight, but it is extremely fuel inefficient. A high-bypass turbofan, the kind used in commercial airliners, moves an enormous amount of air at relatively low velocity through a large fan driven by the engine core. This is highly fuel efficient but cannot produce the specific thrust needed for supersonic flight. Every military jet engine is a compromise between these extremes, optimized for a specific combination of speed, altitude, and mission. The F-119 engine that powers the F-22 Raptor is a masterpiece of this compromise. Developed by Pratt and Whitney and entering service in 2005, it produces approximately 35,000 pounds of thrust in afterburner and around 26,000 pounds in military power, meaning without afterburner. Its bypass ratio of approximately 0.3, meaning for every pound of air that goes through the engine core, 0.3 pounds bypass through the fan, is optimized for the F-22's supercruise requirement, allowing the aircraft to cruise above Mach 1.5 without afterburner at specific fuel consumption rates that the previous generation of fighter engines could not achieve. The F-119 also incorporates two-dimensional thrust vectoring nozzles that deflect the exhaust stream up to 20 degrees in the pitch axis, contributing directly to the F-22's supermaneuverability. It is by any measure one of the greatest military jet engines ever built. But the F-119 is still a fixed-cycle engine. It is optimized for a specific operating point, and while it performs brilliantly near that point, it pays efficiency penalties when operating far from its design condition. An F-22 conducting a long transit at subsonic cruise speed is using an engine that was designed primarily for supersonic performance, and the fuel burn reflects that mismatch. In the Pacific Theater, where combat radii of 1,000 miles or more may be required, and where aerial refueling assets may be contested or unavailable, this inefficiency is a strategic liability. The aircraft either needs to carry enormous amounts of fuel, which means either a larger airframe or reduced weapons capacity, or it needs an engine that can adapt its cycle to the actual flight condition. This is precisely what the adaptive cycle engine does. The core innovation is the addition of a third stream of airflow that can be modulated, increased, or decreased to change the engine's effective bypass ratio in flight. In a conventional two-stream turbofan, you have the core stream that goes through the compressor, combustor, and turbine, and the bypass stream that goes through the fan and bypasses the core. In an adaptive cycle engine, a third stream can be directed to either mix with the bypass flow to increase overall airflow and efficiency, or can be redirected to provide additional cooling for the engine core and exhaust system. By varying the third stream, the engine can shift between a high-thrust, low-bypass configuration for combat and sprint phases and a high-efficiency, high-bypass configuration for cruise and long-range transit. The same engine serves both missions without compromise. The program that developed this technology in the United States is the Adaptive Engine Transition Program, or AETP. Congress funded AETP in 2016 as a competitive development program. with both GE Aerospace and Pratt & Whitney building full-scale demonstrator engines. GE developed the XA100 and Pratt & Whitney developed the XA101, the X designation indicating experimental status. Both engines were tested extensively at the Arnold Engineering Development Complex in Tennessee, the premier propulsion test facility in the United States, which can simulate the altitude and temperature conditions of any flight regime from sea level to above 80,000 feet. The test results demonstrated that adaptive cycle engines could deliver fuel efficiency improvements of 25% or more compared to the F-135 engine in cruise conditions, while simultaneously providing 10% more thrust in combat mode. Those numbers, 25% better fuel efficiency and 10% more thrust, are not incremental improvements. They are transformational. A 25% improvement in cruise fuel efficiency translates directly into a 25% increase in combat radius for the same fuel load, or the same combat radius with 25% less fuel, which means a smaller, lighter, cheaper aircraft. In the context of the Pacific Theater, where the distance from potential operating bases to potential conflict areas can exceed 1,000 miles, this improvement is the difference between an aircraft that can reach the fight and one that cannot. The 10% thrust increase means better acceleration, higher sustained turn rates in combat, and more margin for the high-energy maneuvers that determine the outcome of within-visual range engagements. The thermal management capability of the adaptive cycle engine is a second critical advance that does not get enough attention. Modern combat aircraft generate enormous amounts of heat from their engines, from their avionics, from the aerodynamic heating of high-speed flight, and increasingly from the directed energy weapons and high-power electronic warfare systems that sixth-generation aircraft are expected to carry. The F-22 already operates near the limits of its thermal management capacity in certain configurations. A sixth-generation aircraft with more powerful radar, more sophisticated electronic warfare systems, and potentially laser weapons will generate heat loads that exceed what the F-22's thermal management architecture could handle. The adaptive cycle engine's third stream provides a powerful thermal management resource. The additional cool air from the third stream can be used to cool avionics, weapons bays, and other heat-generating systems before being exhausted from the aircraft. The connection between engine thermal management and directed energy weapons is one of the most important and least discussed aspects of sixth-generation aircraft design. The U.S. Air Force Research Laboratory has been developing airborne laser systems for aircraft self-defense, specifically for defeating incoming missiles in the terminal phase of their attack. A high-energy laser capable of defeating a supersonic missile requires electrical power in the range of hundreds of kilowatts and generates significant waste heat that must be managed. The adaptive cycle engine, with its higher overall power extraction capability and its third-stream cooling resource, is an enabling technology for these weapons. Without it, the power and thermal requirements of an airborne laser would be incompatible with a fighter-sized airframe. Leave your like, subscribe, and share. The materials science enabling the adaptive cycle engine is as remarkable as the thermodynamic concept. The turbine section of a jet engine operates at temperatures that exceed the melting point of the metal alloys used to make the turbine blades. The blades survive because they are cooled internally by air bled from the compressor, flowing through intricate internal passages. In an adaptive cycle engine operating at higher pressure ratios and temperatures than previous engines, conventional nickel superalloy turbine blades would fail. The solution is ceramic matrix composites, CMC materials that can withstand temperatures hundreds of degrees higher than metal alloys while being significantly lighter. GE Aerospace has been a leader in CMC turbine component development, and the XA100 demonstrator incorporated CMC components in its high-pressure turbine section. These materials are not just enabling the adaptive cycle engine. They are the reason it can operate at the performance levels it does. The compressor technology in the adaptive cycle engine has also advanced significantly. Higher pressure ratios, the ratio of the air pressure at the exit of the compressor to the pressure at the inlet, produce more efficient combustion and more thrust for a given fuel flow. The F-119 achieves a pressure ratio of approximately 35:1, which was at the frontier of compressor technology when it was designed. The adaptive cycle demonstrators are designed for pressure ratios significantly higher than this. Enabled by advances in compressor blade aerodynamics, blade materials, and the active control systems that prevent compressor stall, the aerodynamic breakdown that can cause an engine to lose thrust suddenly during aggressive maneuvering. The active stability management systems in the adaptive cycle engine use sensors throughout the compressor to detect the early signatures of stall and adjust blade geometry or bleed airflow to prevent it before it develops. The full authority digital engine control system, FADEC, that manages the adaptive cycle engine is itself a technological achievement. The three-stream architecture introduces control complexities that have no precedent in previous engine designs. The FADEC must simultaneously manage the fuel flow to the combustor, the geometry of the variable area nozzle, the position of the third-stream modulating valves, the cooling air distribution to turbine components, the thrust vectoring system, and the power extraction for aircraft systems, all while protecting the engine from operating outside its structural and aerodynamic limits during the most aggressive combat maneuvering. The control algorithms running on the FADEC processors are the product of decades of engine modeling research and represent some of the most complex real-time control software in any engineering system. China's propulsion development for its 6th-generation programs is a critical part of the competitive picture. The J-20's early production aircraft were powered by Russian AL-31 engines, the same engine family that powers the Su-27 family of Russian fighters. Later, J-20 production shifted to the Chinese WS-10C, an indigenous engine with performance broadly comparable to the AL-31 but with improved Chinese supply chain independence. The WS-15 engine, developed specifically for the J-20, is intended to provide performance competitive with the F-119. Thrust vectoring, high thrust-to-weight ratio, and supercruise capability. It has been in development for decades and has reportedly entered limited production, though questions about reliability and durability in operational service have been raised by Western analysts. For the J-36, China will need an engine beyond the WS-15, likely a Chinese adaptive cycle engine program that has not been publicly disclosed, but which almost certainly exists given the scale of Chinese investment in aerospace propulsion. The propulsion gap between the United States and China at the 6th-generation level may be the most consequential technological asymmetry in the competition. American engine technology, built on decades of experience with the F-100, F-110, F-119, and F-135 on investment in CMC materials on the AETP demonstrator data, is ahead of Chinese engine technology by a margin that is difficult to precisely quantify but is widely assessed to be significant. China has consistently found engine development to be its most challenging aerospace technology problem. The history of the WS-10 program, which took decades longer than planned to reach reliable operational status, illustrates the difficulty of developing world-class turbofan technology from a limited industrial base. Whether China can close this gap with the engine required for the J-36 is one of the most important unanswered questions in the 6th-generation competition. The industrial base that will produce adaptive cycle engines for the F-47 is centered on GE Aerospace's facility in Evendale, Ohio, and Pratt and Whitney's facility in East Hartford, Connecticut. Both companies have been investing in the manufacturing processes needed to produce CMC components, advanced turbine blades, and the complex variable geometry mechanisms of the adaptive cycle architecture at production rates. The supply chains for the exotic materials, rhenium, single crystal nickel superalloys, silicon carbide fibers for CMC components, require careful management and strategic stockpiling, as many of these materials have limited global sources. The Defense Department has identified propulsion supply chain resilience as a national security priority, and investments in domestic production of critical materials are part of the broader industrial strategy supporting the F-47 program. When the F-47 eventually enters operational service, its adaptive cycle engine will be the least visible but most essential element of its capability. The airframe defines what it looks like. The weapons define what it can destroy. The stealth defines where it can go, but the engine defines whether all of those capabilities can actually be employed, whether the aircraft can reach the fight, sustain the tempo of operations, and return to base with enough fuel margin to handle the unexpected. Every great combat aircraft in history has been enabled by an engine that pushed the boundaries of what was thermodynamically and mechanically possible. The adaptive cycle engine is that enabling technology for the 6th generation. And the engineering inside it represents a half-century of accumulated knowledge about how to extract maximum performance from controlled combustion at the edge of what materials and physics allow. Leave your like, subscribe, and share. Until next time.